So
We're not doing anything. It was pretty
almost there. So we have the last team, Group C.
All right. Hi, everyone. We want to give a warm welcome and thank you all for being here with us today. We are Group C, and my name is America Embers.
I'm Maurice Wilson.
I'm Tiara Britten.
I'm Cameron Timms.
And I'm Joanne Huang.
This is our presentation on the design of a disposable circumcision clamp in a clinical setting. Our advisors are Dr. Mary Beth Lima and Dr. Carlos Estede, and our sponsor is Dr. Christopher Roth. To get us started, I'm going to quickly go over our outline. We're going to start off with some background and introduction into our project, starting from year 1 to now year 4. We'll go over our problem statement and dive into our engineering design progress, from our measurable objectives to our completed objectives, and then we'll close out with our Gantt chart, budget, conclusion, and some acknowledgements.
So I'm going to give a brief overview of what a circumcision is. A circumcision is the removal of the penile foreskin. This project focuses on the circumcision technique, but there are several different techniques used across the world to perform circumcisions. So as you guys know, this is the 4th year of this project. Team 1, they performed life cycle analysis to determine was it economically feasible to pursue a design of a new clamp. They wanted to know why disposable clamps were not working as well as reusable ones. So they performed that analysis and they determined it was economically feasible. So team 2, they created a prototype and they tested its performance. And then year 3, they established a testing procedure using chicken skin, with also using the prototype that team 2 created. Fast forward to now, our goal is to 1, adapt and refine year 3's testing method of measuring seal strength with human foreskin and chicken samples, and then 2, enhance and optimize the prototype to address any mechanical flaws that we see fit. The GOMCO reusable clamp is the golden standard of circumcision clamps, so it is imperative that we create a prototype that matches its performance or exceeds it.
Our measurable objectives, our main goal is to adapt year 3's testing method used to measure the hemostatic seal strength produced by the circumcision clamps onto actual human foreskin. Once we have perfected this testing method and are able to obtain reliable and consistent data, we can then compare the tensile stress among the 4 different clamps that we have tested. To the right here, we have a picture of each clamp. We also have pass outs here of each clamp. In figure 2, we have our GOMCO reusable circumcision clamp, and figure 3, we have the Centurion disposable clamp, figure 4, year 2's prototype disposable clamp, and figure 5, our year 4 prototype disposable clamp. Once we compare the seal strengths among these clamps, we can then determine if there is a statistical difference among a reusable clamp seal strength versus disposable clamp seal strength using an ANOVA test with a 95% confidence interval.
So for our testing method, we initially wanted to utilize the micro CT with the Devon stage. And so our idea here was that we'd be able to image the internal structure of the seal while also simultaneously performing a tensile test. Unfortunately, we soon realized that this testing method isn't actually well suited for biological materials, and so we instead pivoted towards using the Q800 dynamic mechanical analyzer, or just simply the DMA. This is a precise machine which allows users to measure the viscoelastic properties of both rigid and soft body materials. And so with this testing method, we completed a displacement ramp experiment, which essentially just served as our tensile test. This machine is also analogous towards the Instron. And so to first begin, a preload force of 0.0001 newtons is first applied. From there, the bottom clamp, which is shown in both figures A and B, is pulled downwards at a constant ramp displacement rate of 1500 microns per minute until the seal eventually tears. As with the Instron, we're able to then measure and record a maximum tensile stress, which occurs right before the seal actually tears. And we then correlated this value with the hemostatic seal strength. For this project, we created 5 samples using chicken skin, which are each about 5 millimeters in width, using each clamp.
So this is video demonstration where we create a seal and we use the DMA to analyze it. Here is our testing procedures demonstration video. In stage 1, we harvest the skin from a piece of raw chicken. The raw chicken skin must be fresh in order to be tested. Here, you'll see Maurice remove an uninterrupted section of skin from the drumstick with a scalpel. After that, we move into stage 2, where we turn the skin into a usable sample for the circumcision. Louise spins the sample to the foam board for stability as she excises the extra skin. You will see her use a ruler to maintain clean margins and uniformity. The final step here is to cut an even strip of skin, folded and safety pinned. And now we are ready for testing. And now for stage 3, we load the sample into the clamp. Maurice has already collected the sample for 5 minutes total. After the 5 minutes, the protruding end of the sample is excised to reveal the seal. This step is critical to isolate the seal and test its strength through the DNA. The nut is then removed and the sample is separated from the nut. The sample is now ready to test. And now we transition to stage 4, where we launch the thermal advancement software in the shared laboratory for macro and biomacromolecular research and show them all. Here, Joanne, who was formerly trained in using the DNA, uploads our testing parameters to the DNA machine. In stage 5, we physically load the sample into the DNA clamps. You will see Joanne tighten the upper and lower clamps with the torque wrench. The torque wrench is used to standardize the amount of force used to tighten screws. Here's an image of our fully loaded sample in the DNA machine. Finally, in stage 6, we conduct our DNA tensile test until the sample seal fails. We have a side-by-side view of both the test and the graph being created. Both the strain and the stress data are being recorded live. The seal eventually fails and we receive a finalized strain stress graph for this seal. This concludes our testing procedures demonstration video. Thank you.
So from our results, as you can see in figure 8, we actually found that the performance of the year 2 prototype clamp fell below the performance of our year 4 prototype clamp. This could possibly be attributed to the fact that here in year 4, we were able to actually embed the screw into the base plate, whereas year 2, they just simply left the screw as its own individual piece. From these results, we see that it's vital to actually embed the screw because the user is then able to fully tighten the nut to then create a sufficient clamping force to create a strong hemostatic seal. It's also important to note that our year 4 prototype does have the highest variability and has the highest standard deviation compared to these other clamps. This could possibly be because of the machining method used to create our prototype, as there were several parts of our actual design or of the actual prototype which were slightly unrefined. And finally, we also saw that the Centurion and the Gomco clamps performance were comparable to each other. However, the Gomco clamp does have higher reliability as it has a lower standard deviation.
Now moving on to redesigning. We were able to print a metal version of our prototype, and some of the changes that we made from the year 2 prototype was that we had embedded the MA screw into the base of the clamp. Then also we changed the top nut to a thumb nut for better gripping and support whenever creating the seals. And then also we designed a model to basically display and formulate the detent mechanism that we will be using for our prototype. And then right here in figure 9, you can see the flush mount ball nose spring plugger, which will be our detent for our model. And then also too in figure 10, that is an assembly of our prototype.
For our constraints, these are some problems we faced throughout the year. Our main one being with our materials. Dr. Roth was kind enough to provide us with actual human foreskin samples from his clinic. However, they were very limited in supply because it was based on how often he went through his procedures and the family's consent. We also had some delays in delivery of our materials, such as our Gomco reusable clamp and our year 4 prototype disposable clamp. Our next constraint is the limited testing methods we could use to test our samples. In figure 12, that is the original size of our chicken skin samples. You can see there's a very big size difference between that and our human foreskin samples provided in figure 11. We originally struggled to find a testing method that could work and accommodate with samples this size. However, once we did find a testing method such as the DMA, we did accommodate our chicken skin samples by making them smaller to the size of our human foreskin sample size, so we could test and obtain that data. And then our last constraint is limited area of research on the topic of circumcision clamp seal strength. We just had a lack of resources that we could rely on for background research.
Overseas dependency. Consulting with the company took about 2 weeks, and then it took another 2 weeks to get the prototype here for us to make the needed adjustment for our prototype. And then with manufacturing, so we have printed 2 different base clamps, bases for the clamp, and both of them came back bent in 2 different ways, so we had to fix that. And then also the nuts that we got back from the company, they were a little bit loose, so they were not an exact fit for the M8 screw. And then also too, the nut that I made for the first nut that houses the detent, it wasn't the exact size that I had intended it to be.
So for our completed objectives, we completed city training and received IRB approval to use human foreskin samples in our testing. We also finished a full design of a clamp with a detent locking mechanism. Additionally, we finalized a standard testing procedure that addressed all of Dr. Roth's requests. From this, we were able to build a data set of all the standard clamps using chicken skin.
In the fall semester, we were able to shadow Dr. Roth as he performed a circumcision procedure. We did gain IRB approval to be able to test with human foreskin samples, and we did formulate a redesign of the year 2's prototype. This semester, we were able to test our samples using the DMA, and then also we were able to print a metal version of our prototype, which does surpass the performance of the year 2's prototype.
So this is just a basic breakdown of our budget. For this entire year, we had an allotted budget of $1,200. We actually exceeded this budget by about $157, and so we were given an additional $1,000. So the total amount spent on this project in total is $1,357.18.
So in conclusion, our ultimate goal was for the design to match and or surpass the performance of the Gomco clamp. However, our notable achievements this year were developing a novel testing procedure to quantify a standard performance of the clamps, and also designing and machining an improved disposable circumcision clamp of our own.
Thank you guys for listening.